In this lesson, we'll be looking at separation techniques. In separation techniques, what are we separating in the first place? We recall from our previous class where we talked about element, compound, and mixture. We said that the component of mixtures, because they are not chemically combined, then we can separate them easily using physical method. So the physical method used in separating the component of mixture, those physical methods will be the focus of this lesson. So what are the methods used in separating the component of a mixture? The method adopted depends on the properties of the component. Recall also from our previous class that we said because when a mixture is formed by mixing two or more substances together, because the mixture, the component, do not react chemically. So the mixture formed retain the properties of the component. Because of that, we can adopt the properties of the component and use those properties to separate them from one another. So what I'm saying in essence is the method of separation used in separating the component of a mixture is based on the properties of the component of the mixture. As such, we have several types of separation techniques. And these several types of separation techniques, each method or each technique is based on the characteristic properties of the component to be separated. The table below itemizes different separation techniques and the characteristic properties upon which the technique is applied. We have the first method here, which is more or less like the traditional method of separation used at home. And that method is sieving. The sieving is used to separate component of mixture based on particle size. That is, you have a mixture of two or more components whereby the size of the particles of the component differ from one to another. Then you can adopt a method known as sieving to separate them. What do I mean? I have a mixture of a powdery substance, for example, like semovita. If you're in Nigeria, you know what I'm talking about, semovita. It's powder. Okay, let me use flour that is universally known. The components, you have a mixture of flour and rice. You have flour that you want to use in baking, and then by mistake, some rice pour into it. How would you separate the flour from the rice? The method known as sieving can be used to separate the flour from the rice. And that method is based on particle size. The particle of flour is far, far, far smaller than the particle, than the seed of rice. So you can apply sieving to separate that. And what is a sieve in the first place? A sieve is a special separating technique that uses the item name is a sieve, something like this, like a bowl. But under the bowl, you have a cloth that has mesh or holes, several mesh or meshes, if there's anything like that. Meshes. I'm going to show you the diagram of first now, something like this. And under this, you have a cloth here that has several holes, tiny, tiny holes, such that when we put a mixture of semo or mixture of flour into this and shake it, all the particles that are smaller than the mesh size will pass through the holes or through the mesh, while the particles that are bigger than the mesh size will remain inside the sieve. So, in essence, the separation technique known as sieving, the properties upon which the technique is applied is solid of different sizes. Because you have mixture of rice and flour, for example, both of them are solid. One has smaller size than the other. So anything that is smaller than the size of this mesh will pass through it inside the mesh or inside the sieve. That method of separation is called sieving. Something like, let me show you the ring. There's a sieve. Okay, look at it here. Sieve here. So this cloth here is a special cloth with holes. It is formed by intersection of holes, section of holes. So it can pass through it easily. While anything that is bigger will remain inside the sieve. The particle size is a property upon which sieving technique is used to separate mixture. The next one is magnetic separation. Magnetic and magnetic solid. A magnetic solid is a solid that can be attracted by a magnet. When a magnet is brought closer to some solid, there is force of attraction between the magnet and the material. And such magnetic solid are, of course, metals. So if, for example, I have maybe something like facial powder or any powder or any substance at all. Let me use facial powder as an example. This is my facial powder in a container. I love to rub powder, maybe for example. And then I have somebody that I feel like, okay, let me just boil this powder for this man. And then the person put pieces of iron filings into my powder. This is my powder. Then this tiny, tiny thing I'm drawing now are iron filings inside the powder. And I love this powder so much that I don't want to throw it away. Huh? What will I do to separate my powder from the iron filings? What I simply need to do is to look for a magnet and place it over the powder. Of course, all the iron filings within the powder will be attracted to the magnet, leaving the powder behind. So the property upon which this method of separation is based is magnetic solid from non-magnetic solid. Now, if you see those malam that go from house to house looking for metals to go and say, you see them dragging one magnet on the floor. Why are they dragging that magnet on the floor? They just want to pick pieces of metals from the floor. Because any metallic object that is on the floor that is in contact or close to that magnet will be always attracted to the magnet. So that is the method of separation they are using in operation there. There's picking magnetic substances from the floor, from non-magnetic substances. Then another method is sublimation. Sublimation is a special method of separation based on solid which sublimes from solid which do not sublime. Now, what does it mean to sublime? Sublimation has to do with a change of solid from solid state directly to gaseous state, change from solid state directly to gaseous state without passing through the liquid phase, without passing through the liquid phase. Now, that kind of change is called sublimation. The normal route for change of state is supposed to be from solid to liquid and then to gas, like water. But there are some solid that doesn't behave like this. When you heat them up, instead of going through the liquid phase first, they go directly from solid state to liquid to gaseous state rather, without passing through this state. Such phenomenon is known as sublimation. But there are few solids that behave like that. Example is iodine. So if, for example, I have a mixture of iodine with some other component that I want to get them separated, then I can heat up the mixture. The iodine will sublime. That is turning directly to gaseous state without passing through the liquid state. We're going to look at each of these methods one after the other. It's just like this table is just like a summary of all the separation technique we are going to discuss. Okay. So decantation is another one. Decantation is used to separate insoluble solid from liquid. Now, when we say insoluble solid, we mean solid that do not dissolve in a particular liquid. So if, for example, I have a mixture of gari that we drink, put gari inside water. You are not in Nigeria, you may not understand what I'm talking about. Gari is a special food in Nigeria that we soak in water before drinking it. Of course, it's a solid, it doesn't dissolve in water. The essence of soaking it is to make it soft before you drink it. So we normally do what we call decantation before drinking it because this gari has chaff. Now, when you put it in water, the chaff always floats to the surface and you allow it to settle a little and then bend the cup in a gentle way to remove those chaff from the surface. What you are doing is decantation. You can do that in the lab also as a method of separation. It's used to separate solid from a liquid, insoluble solid from a liquid. Insoluble is the key word here. That is solid that do not dissolve from a particular liquid. So you may have a cup like this, and in this cup, you have some solid with water inside. Of course, normally gently tilt the cup so that the liquid on top can then flow out, leaving the insoluble solid in the cup. That method of separation is decantation. We're going to look at it in detail. There's a technique or there's an approach in doing that, making use of glass rod and all of that, which we'll look at later. Then filtration. Filtration is used to separate insoluble solid from a liquid also, insoluble solid from a liquid, using a filter paper, a special paper called filter paper. We're going to look at that in detail also. They also have centrifugation, which is also separating insoluble solid from a liquid. Now, what this table is kind of doing is a kind of summary of all the method of separation. We are going to cover each of them one by one. And we're looking at the technique of separation and the properties upon which the method is adopted. Okay? So centrifugation, the method or the properties upon which the method is using insoluble solid from a liquid. For example, you want to separate the component of blood, human blood, or any type of blood, which is made up of plasma, which is a liquid component of the blood, and then the blood cells and platelet, all of them, which are the solid component. To separate the two, we make use of centrifugation. The blood cell has solid component, the plasma is liquid component. So centrifugation is based on what? Insoluble solid from a liquid. Then we also have evaporation, crystallization, fractional crystallization, and precipitation. All of these methods are based on soluble solid from a solution. Now, soluble, that is the solid dissolved in that solution. And so you want to remove that solid from that solution. Any of these methods can be used, either evaporation to dryness if the solid is not affected by heat. And if it is affected by heat, and you can adopt crystallization. And if it's a solid that is in a solution or liquid that is in a solution that is in a way that the what do I call it? Ordinary crystallization cannot handle. Then use fractional crystallization. Then precipitation is also separating a soluble solid from a solution based on the fact that that solid is soluble in one liquid but insoluble in another liquid. Then let's assume I have this is A and then this is B. A is a solution of that solid, a soluble solid plus this solution A. Now, the soluble solid that I put in this solution A, if I put it in solution B, it becomes insoluble, doesn't dissolve in solution B. And so I will make use of that advantage by pouring solution B into solution A. The moment I pour solution B into solution A, the solid present in solution A turn to solid immediately by precipitating out. That is going to form particles that I can filter out of the solution. That method is called precipitation. We'll look at it in detail also. And you have distillation, which is used to separate solvent from its solution. That is, you have a liquid that is within a liquid. Then you want to separate one liquid from another liquid. That is miscible liquid, for example, ethanol and water. Ethanol and water, when you put the two together, they mix completely in a way that you can't tell the difference between the two. If you want to separate that kind of a mixture of two liquid, miscible liquid, what would you use? You can either use distillation or fractional distillation, depending on the boiling point. If the boiling points are far apart enough, then simple distillation is enough to separate one from the other. For example, the boiling point of ethanol is 78 degrees Celsius, while the boiling point of water is 100 degrees Celsius. These are far apart enough. So if you have a mixture of ethanol and water, and you want to remove ethanol from water, then distillation can do that effectively. We're going to look at that in detail by separating solvent from its solution. Now, where the boiling point are close together, then simple distillation won't do that. You use fractional distillation in that case. And the difference is that simple distillation, there's no fractionating column, while fractional distillation, there's a fractionating column. Again, we are going to look at that in details. Then using separating funnel adopts the properties of immiscible liquid. Immiscible liquid, that is liquid that do not mix together. Good example is oil and water. Whenever you put oil into water, you see that the oil will always float on the surface of the water. This type of liquids are described as immiscible liquid. Immiscible means cannot mix. Things that cannot mix together. Immiscible liquid. To separate such liquid, mixture of such liquid from one another, we make use of a separating funnel, special type of funnel that has a control valve, something like this. Then here you have a control valve attached to it. And when you have the mixture of oil and water inside here, for example, usually the oil will be on top while the water will be below. So that when you open up this control valve, the water will flow out, leaving the oil. Of course, this glass is a glass funnel, so it's transparent. You can see a distinct layer of water and oil separated out, so that when you open this valve to let out water, you watch it closely, such that the moment all the water comes out, you just close the valve immediately, leaving the oil behind. We are going to look at that in details also. And the last one is chromatography, which separates solids from a solution. A solid is a solid that dissolves in a solution. Perfect example here is separation of component of ink. Ink as a substance or as a mixture is mixture of several colors. So if you want to separate the colors from each other, then we can make use of a separating technique called chromatography. So like I say, let's look at each of them in detail now. Sieving as a separation technique. So this technique is used for solid particles of different sizes. For example, a mixture of stones and powdery substance can easily be separated with sieving. The mixture to be separated is usually placed here in this compartment, or what I call it now. This cloth, there is a cloth that has several holes, such that anything that is smaller than the hole can pass through, while the one that is bigger than the hole will remain inside here. And these holes are called mesh. So the method or the property used here is particle size. So the mixture is placed over with placed on a sieve with a mesh of a particular size. Particles that are smaller than the mesh size will pass through the sieve, while the ones bigger will remain on the sieve. We do that even at home. The magnetic separation, as I explained earlier, is based on magnetic substances from non-magnetic substances. For example, if you mistakenly put some iron filings in your facial powder, you can easily separate the mixture by placing the magnet over the mixture. The iron filings get attracted to the magnet while the powder remains behind. The sublimation, as I said, some substances sublime. There is a change from solid state directly to gaseous state without passing through the liquid state. An example of such substances are iodine and ammonium chloride. Ammonium chloride, when you heat it up, instead of changing to liquid phase, it goes directly to gaseous state. So if you have a mixture of ammonium chloride and another substance that you want to separate, you can make use of sublimation. That is heating up the mixture. The ammonium chloride will turn to vapor or turn to gas, leaving the other substance behind. Here's a diagram representing that method of separation. What we have here is impure ammonium chloride, and inside a container, then you have an inverted funnel that cover it. The essence of putting this inverted funnel, because this place will be covered with a cutting to prevent the sublimate from escaping if you are interested in the sublimate also. But if you are not interested in the sublimate, you can leave it to escape. To cover this side with cotton wool. Then, once heat is applied here, the ammonium present in this impure ammonium chloride, the ammonium chloride will turn to gas immediately, and the gas is collected here. Because this place is relatively cool than this place. So as it gets here, the temperature is not that high here. So it turns back into solid and then attach itself here so that the impure substance or the impurity rather remains behind. The impurity remains behind while the pure sublimate or the pure ammonium chloride is collected here. Okay, now another method of separation, as I explained earlier, is decantation. Now, decantation is used to separate solid particles from a liquid. Now, if you have a mixture containing a liquid and solid particles, which usually form separate or which separate into two distinct layers on standing, There is a lower solid layer and an upper clear liquid layer. Using a glass rod, the upper layer of clear liquid can be carefully poured or decanted into a second container. This is a quick but inaccurate method of separating the component of a mixture. Now it is inaccurate because while decanting the clear layer of liquid, some particles of the solid may also follow that clear layer of liquid. And that's the essence of having this glass rod here, so that any particle of solid that escape from this cup here will, this glass rod will prevent them from entering into this container. Of course, some of them may eventually enter. That is why we say it's inaccurate method of separation. Okay, so here is a simulation of decantation. You can see this test tube here contains a mixture of a substance that does not dissolve in this solvent or in this liquid. Now, when you leave it on standing for some time, because the solid does not dissolve in the solvent, it will form a distinct layer. The liquid will be on top of the test tube. That is what I represent with those black particles inside there represent the undissolved solid, while this upper part represent the liquid. So that once they separate into two distinct layers, we can carefully pour the liquid layer out, leaving the solid particle behind. So let's watch a simulation on that. These are two distinct layers of the liquid and the solid. The particles on that represent the solid, while these all represent the liquid. So that when we pour it gently, the liquid can escape, leaving the particles behind. That kind of inaccurate method of separation is called decantation. The essence of this glass rod is to prevent if any liquid, if any solid particle escape from this test tube, this glass rod can prevent them from entering into the container. Of course, part of it may eventually enter into the container. And that is why we say that it's a quick method of separation, however, it is inaccurate. That is decantation. Now we have another method of separation which is called filtration. Now filtration makes use of a porous material like a filter paper. A filter paper is a special paper, a porous paper that can separate insoluble particles from liquid. For example, a suspension of chalk dust in water. Now, when we say suspension, if you grind chalk powder into powder, and you pour it into water, it will form a suspension because the powder is not going to dissolve. So when something like that inside water does not dissolve, what you have is a suspension, not a solution. Water pack, leaving the chalk behind. We need a special paper called filter paper. Now, filter paper will allow water to pass through, leaving the chalk powder behind. So, for example, the suspension of chalk dust in water is poured onto a filter paper. The water passes through, leaving the chalk particles on the filter paper. A good use of filtration is in water company. Water purification plants and breweries make use of filtration to remove solid particles from liquid. As water company, before they package the water, they have to do a lot of purification processes. And one of the process is filtration. Now, again, I have simulation on that. Let's go and watch it also. Okay, so here are filter papers. We have these papers in the lab that are used for filtration. So there are steps involved. First of all, you pick up one filter paper, then this line I drew at the middle, you fold it on that. You just use it as a representation. It's not as if the filter paper has a line there. That is, before you do filtration, you have to fold it into two here, as seen here. You can see that I have kind of demonstrated the folding here. Then once you fold it like this, you fold it again. Look at it, the second line there. Let's look at that again. This one, the first folding is to fold it into two halves. Then after that, you fold along this part again to form this type of shape. Then you hold it and gently open it to form a funnel-like shape, like something like this. You know, when you fold it twice like that and you open it at the middle, You are going to have something like this one here. Then you get a funnel, put the funnel inside the test tube, then insert the folded filter paper into the funnel. Then the substances to be separated, which is this test tube up here containing the colored or the suspension of chalk. This colored liquid now represent the suspension of chalk or chalk suspension. By the time we pour it over the filter paper, you can see, watch it, you see that water is coming out. Now, of course, it's going to be a clear water, clear layer of water. Now, it's not going to be colored like this. But if I make it clear, you may not be able to see it. That is why there's a little color. Now, what I'm saying in essence, this filter paper is so accurate that if you use it to filter chalk suspension, the water that is going to come out in this test tube will be clear, colorless, like the normal water, like drop, drop by drop, like that, leaving the chalk particles on the paper while the water comes into the test tube. So that is filtration method used in the lab. The industrial one make use of a filter bed, which is far bigger than. The next one is centrifugation. Centrifugation is based on centrifugal force. As when something rotates in a circular pattern, two forces are acting on that thing. Now, this is a circular path that the object in a circle is wonderful. Let me try and drive that down. For something moving in a circle like this, two forces are acting on that thing. There's a force that is pulling the thing towards the center, and that force is centripetal force. And there's also a force that is pulling it away from the center of the circle. That force is centrifugal force. So centrifuge or centrifugation is based on centrifugal force. Use that method to separate solid particles from liquid. And a centrifuge is a machine which can spin test tubes containing suspension at a very high speed. So if I have a test tube, maybe containing a suspension of chalk or blood, I love using blood here because centrifugation is used extensively in the medical lab to separate blood blood component that is separating plasma from or serum from blood cells and platelets. So if I have blood in this test tube and I want to remove the plasma, which is the liquid, I need a centrifuge machine. The centrifuge machine is designed in a way that you have slots for test tube, slots for test tube. These are slots for test tube. So we can insert a test tube here, insert another one, insert another one, insert another one. Then all of these slots are attached to a spinning wheel that can spin at a very high speed. The spinning wheel here can spin at a very high speed. So as a spin, the test tube containing the suspension, all the solid particles in that suspension will settle to the bottom of the test tube, while the supernatant layer, the clear layer, will be the liquid component of the suspension. So that kind of a separation method is made use of in the hospital and medical lab to separate blood cells from blood plasma. I have a simulation on that. Let's watch it. Okay, it's just a schematic representation of what happened in real life. See the real test tube here by the left hand side. And see it here, there are test tube inside the centrifuge here. Is a real life centrifuge here. What I have here on the right hand side is just a schematic representation of what is going to happen inside the test tube, the centrifuge machine. So this test tube, we insert this one here, insert this one here, insert this one here. So let's look at it. You see, I'm depicting that. Inserting the test tube, then we cover it. Cover it. You can see now we're spinning it at a very high speed. We're spinning right now at a very high speed. Spinning, 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 spinning. Then the spinning is done. You can see now the blood has been separated into components. The dark component is a blood cells, while the supernatant layer that is what color is this? Light yellow represent the blood plasma, which is a liquid component of blood. So now what separates this is the centrifugal force. The centrifugal force push all the solid component to the bottom of the test tube while the liquid layer remain at the top. This liquid layer at the top, we call it the supernatant layer. Okay, now this supernatant layer now can be decanted, which is a method of separation we talked about earlier. Just decant it gently. to make use of whichever analysis you want to do. So we are removing the test tube now. Okay, that is centrifugation. Okay, so the next method of separation is flotation. Flotation is used to separate metals from their ore. Most metals are obtained in form of ore, a metallic ore, and metallic ore is an impure metal. So to remove the metal in its pure form, you need a method of separation, which is called flotation. So metallic ores are found in nature in low concentration. Now these are usually sulfides mixed with earthly materials. And before the metals in such an ore concentrated, concentration is often accompanied by a process called flotation. Now, how does flotation work? The low-grade ore is ground into fine powder. You have to grind it into fine particles first. Then you mix it with water and air to form a kind of foamy, frothy mixture. Now, the water-wetted particles of rock and earth settle to the bottom of the container, while the unwetted metal particles or the ore particles is not yet the metal in its pure form, the unwetted one will float to the surface. That is why the name flotation. The ore is made up of different nonsense, the earth and other impurity. So when it is ground and mixed with water and air to form a foamy substance, the metal will float to the surface because it's not wet, while the impurity will go to the bottom of the container. So the metal that floats to the surface can be scooped or filtered up using whatever method of filtration that you think is suitable for that. Now, I did not prepare any simulation for that. There's no yeah. So I have to move on to evaporation to dryness. Now, evaporation, which is a method you can even do in your kitchen, has to do with boiling of a solution in a way that the liquid component of that solution evaporates, leaving the solid or the solid component behind. Evaporation can be used to recover a solid or solute from a solution. And a water bath or sun bath is used to bring about a steady rate of evaporation. Now, what is water bath or sun bath? If I have a container like this, and I have salt solution, because evaporation will do that for me. Most container, rather you place this container in a water bath. There is another container containing water. So a bigger container, for example, containing water. So this bigger container will apply heat to. The essence of doing that is so that the heat will be evenly distributed on the container inside. So if you apply heat directly to this, of course, anything here that is in contact with the heat will receive more heat than those one away. So to bring about a steady rate of evaporation, we put the container inside a bigger container containing either water or sand. When it contains water, we call it water bath. If it contains sand, we call it sand bath. That's just what it means. So we put the container containing the solution inside a bigger one, then apply heat to the bigger one to bring about a steady rate of evaporation. So the liquid in this solution will evaporate, leaving the solid behind. Now, this method of separation is used to prepare salts, but not all salts. It's not suitable for salts that are destroyed by heat. There are some salts that are destroyed by heat. So such salts are separated using crystallization instead. We'll look at that later. So now I have a simulation for evaporation. Okay, so let's start from the beginning. This is the water bath in this case. There's no way I can put this container here. That is why I just left it on top. The right thing to do is to put it inside this water so that this become water bath while this is the salt solution. So there will be steady rate of evaporation. Now let's watch what is going to happen. We'll heat up the water. So we're heating now. We are heating, we are heating, we are heating. The water is boiling. That is what I'm depicting with these bubbles. These are bubbles of water. Now you can see that something is forming in the upper container. The water is reducing while some white substances are being formed. That is the salt that is coming. The water has evaporated. It appears after the evaporation. Let's do that again. Usually, this container containing the salt solution should be put inside this water bath. The lower container represents water bath, which will contain water or sand. When it contains water, it's a water bath. When it contains sand, it's a sand bath. Now, salt solution on top, the heat is applied to the container under. Look at it. As the water in the container is boiling, the heat is transferred to the container containing the salt solution. And then this one also begins to boil so that the water can evaporate at a steady rate of evaporation. And then the salt appears. Another method of separation is crystallization. Like we said, that for salts that are affected by heat, we can't use evaporation to separate them from their solution. Rather, we do crystallization. The process is almost similar. The only difference is that evaporation to dryness, we are applying heat to the solution until the water in the solution dries up, leaving the salt behind. Crystallization is a little, but not until the whole water dries up. Now, how do we do that? This is a container containing the salt solution. Here's my salt solution. My salt solution is right there. It's a concentrated salt solution. Because this salt in here is affected by heat, I cannot use what? Evaporation to dry it. Rather, I use crystallization. Now, what I do is to heat up this salt a little and then remove it from the source of heat and allow it to cool. As it cools down, crystals of salt will be forming out in this solution. And to speed the rate of crystallization, there are things we can do. And those things are what? You can either scratch this to act as a center of crystallization or adding a sample of the salt into the solution, which we call seeding. That is, seeding is what? Adding a little crystal of the salt into the solution to speed up the rate of crystallization. Now, examples of salt that are separated using this method are copper 2 sulfates, that is copper 2 tetrasulfate 6 pentahydrate, then copper 2 triethylnitrate, 5 trihydrate, and iron 2 tetrasulfate 6 heptahydrate. So we cannot separate them by evaporation to dryness. Rather, we use crystallization. Again, I have a simulation for that. So let's watch it and see what happens. Okay. Again, we place the container containing the salt to be separated. This is a solution of the salt. As a salt solution set on water bath. We place it inside water bath, but yeah, place it on top because this container is bigger than it, clearly. As I have to place it on top, and then the heat is transferred to the salt solution on top. Look at it. We heat it for some time. Remember, it's not evaporation to dryness we are doing it. We just want to heat up this salt to kind of saturate the solution. Because if you heat it to evaporation to dryness, the salt inside is affected by heat. It will be decomposed. And we don't want to decompose the salt. We just want to remove the water or remove the salt rather from the water. So we heat it up to saturate it. Look at it. Salt solution is allowed to heat up for a while. Then we remove it after it's heated. Okay. Now we have removed the salt solution from the source of heat. Now we allow it to cool. Now, as it cools, you see that crystals of salt will be forming. You see, crystal of salt is being formed, and crystals of salt is being formed as it cools. Now, to speed up this, that is crystal formation. There are two things we can do. Either seeding, that is adding, if you have already the crystal of this salt available, you have it, you can add a little of it into it. As the water cools, just add a little of the crystal of salt into it. That practice is called seeding. You are adding a seed of the salt into the solution, or you scratch the inner surface of the container. Now, I decided to use a glass container here. There's no glass we use in the lab. There is a special thing used for this, a ceramic plate actually. I just want us to be able to see through what is happening. That's why I decided to use a glass here. Okay, so look at it. You see the crystals of salt is already formed. So we can have use filtration to remove the crystal of salt, which we already described. We described that filtration as a method of separation in the previous one. So just pour this water now with the crystal into filter paper, of course. The water will pass through, leaving the crystals on the filter paper. Can now dry the crystal in a desiccator. Now, where ordinary crystallization is not enough, then we can use fractional crystallization. which is used to separate two or more solids which are present in the same solution in roughly equal amounts. And the solubility of different solutions or solids in the given solvent must differ at different temperatures. Here, if I have maybe salt A plus salt B inside this container, the solution, these two salts are present in this solution here. Now remember that before the crystals are formed, now when you heat it and allow it to cool, as it cools, salt A has a different solubility from salt B. What do I mean by different solubility? At the temperature at which this salt will remain as a solution here is different from the temperature at which salt B will still remain as a solution within this. Now let's assume the temperature at which this one will crystallize or turn to solid 50 degree, 50 degree, while the temperature at which this one will turn to solid, remember both of them dissolve in this solution here. So they are now in liquid form within this solution. Or want to get them back in solid form, they have different solubility, temperature at which they remain dissolved. This one is 50 degree. Now this one is, let's say 40 degree. So when you heat up this to a certain temperature, then you bring it out now, allow it to cool. As it cools down, of course, the temperature has to get to 50 degree before it gets to 40 degree. So once it gets below 50 degree, this salt A will no longer remain as liquid within this solution because the solubility, the temperature now is below the solubility. So it begins to crystallize out of the solution that is turning into solid particle within the solution before this salt B, because the solubility of salt B is lower than the solubility of salt A. So once the temperature falls below this one will crystallize out of solution before this. Before this one will start crystallizing out of solution, temperature has to go below 40 degrees. Once the temperature falls below 50, from 50 down to 40, anything that crystallizes out should be salt A. Then the moment it falls below 40, anything that crystallizes out should be salt B. That is fractional crystallization. Okay, the next method of separation is precipitation. Precipitation. Now, precipitation is used based on a solid that dissolves in one liquid but that doesn't dissolve in another. Some liquid will dissolve them, some other liquid will not dissolve them. So we can use that method to separate such solid iron 2 tetrahydrosulfate 6. Iron 2 tetrahydrosulfate 6 can dissolve completely in water, but it doesn't dissolve in ethanol. So if I have iron 2 tetrahydrosulfate 6 in a solution, as I put it in water, it's going to dissolve to form a solution of iron 2 tetrahydrosulfate 6. Here is the solution of iron 2 tetrahydrosulfate 6 with this test tube. Now, I want to recover this iron 2 tetrahydrosulfate 6 from this solution. What am I going to do? I cannot evaporate this to dryness, but this salt will be decomposed by evaporation. So what will be the best method of separating such? I can make use of precipitation, because this is soluble in water but insoluble in ethanol. So what I need to do is to pour ethanol into this solution. The moment I pour ethanol into this solution, the iron sulfate will precipitate within the solution. And what is precipitate? This is going to turn back to solid within this solution. We're going to form particles of solid within this solution such that I can just filter out the particles of the iron sulfate. Just filter it using filtration method. Again, I have a simulation for that. Let's go and watch it. Okay, so look at this. This container, this bigger container here, this is a solution of iron 2 tetrahydrosulfate 6. And see it dissolve completely in water. That is iron 2 sulfate mixed with water is what we have in this bigger container. It dissolve completely in it, but I want to recover that iron 2 tetrahydrosulfate 6 solution, solid rather, a smaller test tube containing ethanol. Iron 2 sulfate doesn't dissolve in ethanol. So the moment we pour ethanol into this solution, the iron sulfate will precipitate within the solution. It's going to turn to solid particles within the solution. Let's watch and see. Okay, all the ethanol poured, you see? You see particles that are forming inside. These are the precipitate of iron 2 tetrahydrosulfate 6. So those precipitate now Once they are formed completely, we can filter them out using filtration method and then dry the precipitate or the particles of substance to get the ion sulfate. So that method of separation is precipitation. Those particles that are being formed are the precipitate of ion 2 sulfate. Okay? So the property here is the fact that ion 2 sulfate is soluble in water but insoluble in ethanol. However, water and ethanol are miscible liquid. That is, they are liquid that mix completely. The solid here is the iron sulfate. It is soluble in water but insoluble in ethanol. So we pour ethanol into the solution of iron sulfate to cause iron sulfate to precipitate out of the solution. You see the precipitate? So we can filter this precipitate using filtration discussed earlier. Okay, so that is precipitation in action. Let's move on to another method of separation, which is distillation. And distillation is used to separate miscible liquid and is based on difference in boiling point. If you have two miscible liquids that have widely, unduly far apart boiling points, then we can use simple distillation to separate such liquid. A good example is a mixture of ethanol and water. Ethanol and water are miscible liquid. That's, you can mix them and they mix completely. I wrote ether instead of ethanol. And therefore, let me write that. Ethanol and water. They are what? Two examples of miscible liquid. Miscible liquid are liquid that are mixed together completely. When you pour ethanol into water, both of them will mix completely in a way that one will not be able to distinguish one from the other. Those type of liquid are called miscible liquid. So if the boiling point of the two liquids are far apart, then we can use distillation to separate them. For example, the boiling point of ethanol is 78 degrees Celsius, while that of water is 100 degrees Celsius. So to separate these type of liquid from each other, we can use distillation. Using the distillation apparatus, which is a setup like this: a round bottom flask, a source of heat, and a stand, a condenser. This condenser, you can see there's a pipe inside, then there's a pipe outside. The outer pipe is designed in a way that you can pass an inlet. This is an inlet that allow cool water to go into this place. As the cool water goes into this place, it cools the inner pipe. As it cools the inner pipe, the water comes out here. So as we boil the mixture, here's the mixture here. As we boil the mixture, because when boiling takes place, whatever is here will turn to vapor. Whatever is here will turn to vapor. So that the gas will come pass through this pipe, inner pipe. Now, when it gets into this condenser, because of this cool water that is being passed into the condenser, the gas will turn to liquid, and then the liquid will come out in this container. Now, we said that we use it based on boiling point. So for ethanol and water, they have different boiling points. If we apply it here, ethanol will boil first because it has a lower boiling point. So whatever is coming out at a temperature between or from 78 degrees downward, anything that comes out here is definitely ethanol. So the temperature is 78 degrees. So as it boils, it turns to gas and comes out through this pipe. And then it's collected in this container, which we call the distillate. That is, whatever is collected there is called the distillate. Once all the ethanol boils off, then you can remove this distillate and then use another container to collect the water if you're interested in collecting the water or whatever is left behind. Now, where the temperature or where the boiling point is close, then we can't use simple distillation. Rather, we use fractional distillation. And then the difference between simple distillation and fractional distillation is that a fractional distillation contains a fractionating column. A fractionating column, the one we use in the lab, just a special container that is filled with pieces of glass here, pieces of glass. Now this fractionating column is attached to this container here, this round bottom flask. So attached to it, such that the vapor that is coming out of this place, first of all, goes through the fractionating column before coming into the condenser. So as it goes into the fractionating column, the temperature there is lower than the temperature of the container. And so, because this liquid boiling point that are close, as this one at 78-degree boil, it could be that a little of this will also boil and goes into the fractionating column. But because the temperature in the fractionating column is lower than the temperature in the container, and the boiling point of this is not yet reached. So once it gets into the fractionating column, it turns back into liquid and falls back into the container. Why the one that the boiling point is already reached, it goes into the condenser and then comes out as a distillate. Let's go and watch the simulation of that. So first of all, simple distillation. Okay, here's the mixture to be separated in this round bottom flask. You can see a thermometer attached to the round bottom flask. The thermometer is to read the boiling point of the mixture, the component of the mixture. So in this case, let's assume this is a mixture of ethanol and water. So the moment we heat it up, because the boiling point of ethanol is lower than the boiling point of water, the ethanol will boil first. So as it boils and turns into vapor, the vapor will go through this condenser. As it enters into the condenser, cool water is coming in, turns back into liquid, and is collected as a distillate in this conical flask. Let's watch and see what happens. You can see the mixture is boiling, you can see gas is rising up, and you see the gas represented with this arrowhead. Now you can see the distillate is coming out in this conical flask. So this will continue until all the ethanol in this container boils, and you can, of course, look at the temperature. Anything that is coming out from a temperature of 78 degrees is definitely ethanol, because the temperature of the boiling point of ethanol is lower than that of water. So once the temperature, as long as the boiling point, or the temperature rather, as long as it remains at 78 degrees, anything that is coming out here is ethanol. Simple distillation in action. The mixture here in the round bottom flask, and here is a fire burning to boil up the mixture. As it boils, the one with lower temperature turns to vapor, and you can see the gas that is coming out, and the gas gets into the condenser. It turns to liquid and flow into this conical flask. Let's see that in action again. Now the mixture is boiling and turning into gas. The one with lower boiling point is the one boiling right now. It turns into gas and is then goes into the condenser, turns back into liquid, and then is collected in this conical flask. This one that is collected here in the conical flask is called a distillate. Okay, so that is simple distillation. Now let's look at fractional distillation. Like I said, the difference between the two is that simple distillation is used for separating liquid that, if the boiling point are not far apart, we use fractional distillation. The fractional distillation contains the apparatus has a fractionating column. So let's look for that fractional distillation. Okay, here is a setup of fractional distillation. You can see there's a fractionating column here. This thing here on top, and the fractionating column is filled with pieces of glass. So the temperature in the fractionating column is lower than the temperature in the container. So if the boiling point of the liquid is close, then as one of the liquid boils, the one with lower boiling point, as it boils, part of the other liquid may also goes into vapor and then comes into the fractionating column. But because the boiling point is not yet reached, as it comes into the fractionating column, it will turn back to liquid because the temperature in the fractionating column is lower than the temperature in the container. So it turns back into liquid and go back into the container. While the one with lower boiling point will go into the condenser and be collected as a distillate. So let's watch. You see that something is falling back into the container. That is a depiction of a little of the particles or the second liquid that went into the fraction. The boiling point is not yet reached. As it gets into the fractionating column, it falls back into the container. While the other one with lower boiling point still continues its journey as gas and eventually gets into the condenser, then turns to liquid inside the condenser and falls into the conical flask. to be collected as a distillate. That is fractional distillation in action. We use it to separate miscible liquid that have close boiling point, while simple distillation is used to separate miscible liquid that have far boiling point. Okay, this fractionating column and fractional distillation rather is what is used in the industry to separate crude oil. And we have several components. You have petrol, you have kerosene, you have diesel, or lubricating oil. All of these are components of crude oil. Now, these components are separated using fractional distillation. But the boiling point of these components are quite close to each other. You can see what is happening in fractionating column help to return a little vapor of the second liquid that goes up there when the first liquid is boiling. But when it gets into the fractionating column, it goes back because the temperature in the fractionating column is lower than the temperature in this. So there you have it, distillation and fractional distillation. Let's move on to another method of separation, which is a chromatography. Chromatography is used to separate components of something like ink. As you have several types of chromatography. You have the one we use in the lab. It is a simple one called paper chromatography. And the paper chromatography uses a solvent moving over a porous or absorbent medium, for example, a paper. You have a special type of paper called the chromatography paper, and we use it for chromatography to separate a mixture of solids. There are many types of chromatographic procedure. The widely used one is used to separate colored as well as colorless substances. For example, dye, ink, even amino acids. We use it to separate amino acids. Now, how does it work? And let's go and watch the simulation again. So, okay, so here is the chromatography paper. Why this container here represents the chromatographic tank. There's a special tank used for chromatography. I just use this container to represent that. And it contains a liquid, which could be water or any liquid that can separate the component of whatever I want to separate. Now, this liquid is called the mobile phase, while the paper is the stationary. So you take the paper and then make a base, and you dip the paper into the chromatographic tank containing the liquid or the solvent. Now we dip it in a way that the drop of dye is slightly above the liquid. You don't dip the drop of dye with the baseline inside the liquid. It has to be above, slightly above. You look at it, and you have to cover the chromatographic tank to prevent evaporation of the solvent. And as you dip it, of course, the liquid, the solvent, will move up the paper through capillarity. Whereas when water moves like this on a substance, called that kind of action capillarity. That's capillarity action. So look at what is going to happen. Look at it. The water is moving. It's moving over the paper, and it's moving over the paper. It carries the ink particles along, and see that the ink particle is separated into different components represented by different colors. So this method of separation is called chromatography. Now, this thing I'm moving, the ink is made up of different components having different rate of movement. So because of their different rate of movement, as the mobile phase moves over the paper, it carries this component along. Look at it, look at it. That kind of separation is called chromatography. And then finally, the last one is the use of separating funnel. Separating funnel is used to separate immiscible liquid. Immiscible liquid, that's liquid that cannot mix together. And I give example, oil and water. You have oil and water in the same container. There's no way they can mix. So we describe miscible liquid. The oil will always flow on the surface of water. And because of that, you can use a special funnel called separating funnel to separate the water from the oil. Let's watch the simulation. The separating funnel is something like this. Now it has a valve, a control valve that one can open and close to this place. The control valve. This is the receptacle. that can contain the mixture. So if you have a mixture of oil and water inside here, the oil will always be on top while the water will be down, such that when we open this control valve, anything that comes out first has to be water because it's water that is down. The glass is a glass funnel, so it's transparent, you can see through it, so that as you open the valve, the water will come out. When you watch, the moment all the water comes out, then you lock the valve, leaving the oil behind. That kind of separation using this funnel called separating funnel is called the use of separating funnel. And that brings us to the end of separation technique. So in summary, the method used in separating a particular mixture is based on the properties of the component of that mixture. Like this last one we done is, they are immiscible. And so one will separate out on top while the other one is down. So we'll put it in this funnel, allow the one down to flow out, leaving the one on top. Then talking about a mixture of powder and iron firing, of course, we make use of magnet because iron will always be attracted to magnet, while the powder will not. Again, talking about sieving as a method is based on particle size, as of the sea, and so they will pass through the mesh, while the ones that are bigger than the mesh will remain in the sea. In essence, the method used in separating mixture is based on what? The properties of the component of the mixture. So that brings us to the end of separation technique. And then we're going to hang it here for today.